Okay, so the fifth topic, and which is also the last in in this course, the following topics, the embedded systems, actually, that's advanced. And if you want to have a 5 credits, European credits, rather than 3 credits, you can actually learn that yourself, but only after you have done all the first exercises. Only after that. This embedded systems part actually is quite special especially for the Metropolia Smart Systems classes, since it basically teaches how to make the implementations on a limited resources, meaning microcontroller environment. So basically, that's very hardware-oriented programming kind of topic. But if you are into it, yeah, you can go and do your own study on that one based on the material I will be putting there. Since basically it has been a while since I've been lecturing this one before, I would like to make the new material. So you might also want to wait for a few weeks before going there, if you wish to take the 5 credit instead of 3. Okay, and today's topic is about the, where do I open it for? Oh, that one, there. So, IIR filters, it says filter design to just because, well, at some point I might actually also add something about the nonlinear filters. But few words about IIR filters. Infinite impulse response filters have never linear phase response unless you do implementation which is the 0 phase system, meaning you filter the data on both positive and negative time direction. Okay. What is the advantage on IIR over the FIR is that you will get a better amplitude response with a lower number of calculations. So it's more cost efficient, especially with the limited resources, like mobile systems. Okay, what kind of applications it has? Well, there are some here. So, for example, audio filters, they are basically almost always type IIR filters. Well, equalizer, meaning that that's actually a bank of audio filters. So basically, if you have a harmonic equalizer on your stereo, it's basically just a bank of filters. One application is feedback reduction. That was hot topic when these mobile phones were young. So a Finnish company, Nokia, made a big effort on getting the GSM version 2, the line delay. The first GSM versions when your father bought their first mobile phone, they had the feedback so you can hear yourself with the about half-second delay. But then there was this feedback reduction was done for the next generation. And that was done not on the mobile phone, but on the base station side. Okay, so some fancy work was then done for the feedback reduction. High Q factor. Okay, Q factor on filter means how narrow filter you can make. High Q meaning the very narrow bandwidth. Well, Q factor is simply center frequency divided by bandwidth. Okay. What is the KWAT actually on the backside of the IIR filter design is that it's a complex design. It's not that straightforward anymore. The FIR is quite straightforward. You just pick a window or the cutoff frequency for sync. Then you pick the window shape for the stop band attenuation. Then you pick the window width to adjust the this edge of the filter, the transition bandwidth. That's simple. Only those 3 steps, and then maybe modulation, low pass to high pass, or band pass, or that kind of system. So it's very straightforward. But IIR filter design is never such straightforward. But it's not that hard either, since we have these nice tools. 4 methods mentioned here. Then there are plenty of people who are claiming now they have even better than any of that kind of methods, but they usually fall into category optimized. Okay, that's basically ancient history, so-called bilinear transformation of classical, meaning analog filters. Have you got the analog filters on your studies yet? The Salenki filters, operational amplifiers. Are you familiar with operational amplifiers and analog filters? Okay. Don't worry if you are not. So basically, on analog filters, you have the analog filter has also transfer function similar to the digital one, but on analog you don't have the Z plane but S plane, which is well, just different representation. And on S transfer function, you replace S with the 2 over sampling time Z minus 1 divided by Z plus 1. Okay, so it's just a direct replacement of S equals to that one, and you get a Z transformed. So you have a transfer function in the digital domain, except that this one warps the frequency space. Okay, the analog frequencies can go from -infinity to infinity, so there's no limit for the frequency. But on the digital domain, you are basically limited by the sampling rate. So you can only represent signals within the sampling rate over 2. Okay, this bilinear transformation will transfer all of this frequency information. It basically remaps it between minus Nyquist frequency to Nyquist frequency. So in one sense, it takes the minus infinity frequency and plus infinity frequency of the analog domain and warps it like this one, making the unit circle. Okay. Yeah. But anyways, so basically the frequency space is skewed after that one. However, this can be used to transfer any analog system transfer function into digital system transfer function, which is usable in some cases. For example, if you have a high enough sampling rate and you have a slow system in analog world, you can basically use this one to do the modeling of that analog system. So basically, this can be used in game engines where you want to actually simulate the physical phenomena. You have a transfer function of an object in S-plane, use bilinear transformation. Ta-da! There you have for the game purposes. Humans cannot see the difference. It'll be close enough. Okay, another one, the second method, parametric modeling. Parametric modeling, it basically starts with the differential equation of the system of an analog system. And then basically, if you have differential equation, it has these time derivatives, just like the classical, pendulum or clock going like that one with a mass here. You can actually calculate how it turns like this by making the differential equation and solving it. Okay, same thing here. You can base, but now we can take this differential or time derivative of the phenomenon here, and replace it simply by this approximation that dx is actually delta x. So two subsequent samples of data, you just take the difference of them. And then the time difference dx is delta x, which is just a sample time. Okay. This works. You can then have the differential equation turns directly into difference equation. Some caution about that one. So the frequency space is mapped directly with this system. So time doesn't warp, but aliasing effect is here, since you are losing information when you are replacing the derivative with this difference. You just lose information. It's not there anymore. If there was a fastly changing phenomenon on that differential equation, it does not exist anymore on the difference equation. It's the aliasing actually distorts the performance. All right, direct design. So that's actually just taking the system coefficients, start tweaking them to minimize the root mean square difference between desired and real amplitude response. Or take the zero pole plot and start moving these zeros and poles accordingly. That will be basically just a constrained direct design. So you know that if you put a 0 on the unit circle, anywhere on the unit circle on zero pole plot, you will get 0. Okay, let's put a lot of those. You will get 0 response on frequency domain. How many did I put there? 1, 2, 3, 4, 5. So goes to 0. The amplitude response goes to 0 on those points. So you know, okay, that could be a stop band. Then you can start putting these poles somewhere around here, for example, to adjust the gain so that you will get a somewhat the constant ripple on the stop band, and just move them around. You will get a different response. And if you have a routine doing it, you can keep this one on inside of the design box, so to speak. Design box is defined by the cutoff frequency, stop and start frequency, stop and attenuation, and this ripple. So you have 4 parameters, and basically write some sort of routine to do the optimization for you. So directly from direct design, when you automate the finding of this optimal solution, it would be optimized method. Okay. Good. So those 4 methods. This is more like, handwork here. this is with some optimizing routine, minimizing routine. Okay, good. So those filter design methods. We will be using today a couple of, so this is the band stop notch filter, which is basically the direct design. And this is the only IIR filter you can actually do with your paper and pen. The rest of the designs require some tools. So band stop notch filter is a filter where you place a zero and complex conjugate pair on the unit circle. Okay, think of you have some measuring electronics, and you notice that on the data you see humming, line humming, meaning 60 hertz, or actually usually it's 120 hertz first. Why it's double the AC frequency. There's source for error in, or source for the this kind of line humming is not usually that sinusoid, but it's the rectifier. Okay, think of it. So you have 60 hertz AC line, and then you have a rectifier. So the AC goes here. That's the basically neutral and line. So basically, you have the after the rectifier, full bridge rectifier, that you have this kind of, So, okay, as you can see, this is the full cycle. So that would be 1/60 hertz. But the fundamental of this is half of it. So basically what you get is 120 hertz humming. 60 hertz wouldn't actually, you wouldn't hear it. But 120 is actually nasty, since it's about the same as, a human voice, the lowest notes. Your hearing is quite sensitive for checking those noises. So that's why usually you want to get rid of the 120 hertz. So that's 1/120. Okay, so how about designing a filter to take off this humming? By setting a zero exactly at omega 120 equals 2 pi times 120 hertz divided by Fs. So we will put a zero pair on that angle. And let me show you that. Okay, just a moment. I'll do some housekeeping here. There. So this is the band stop notch filter. Stop. There we go. So band stop notch filter. Sampling rate, for example, 2000 hertz. So we have a measuring system, not a audio recorder, but a measuring system, and we want to get the this nasty 120 hertz, which appeared because you couldn't do the power supply correctly, or you bought it the cheapest one you could find from the China. So yeah, there are differences on the cheap electronics and good electronics. You can buy cheap and good, but you have to buy both of them. You usually first buy the cheap one and then you go and buy the good one. All right, so yeah, sampling rate, then we put the 0 on that point, meaning omega of that z equals to exponential of j times 120 hertz divided by sampling rate times 2 times pi. Yeah, that's the what I'm doing here. It's not exponential yet. Sorry. So that's the omega, the corresponding angular frequency, normalized angular frequency. 2 pi 120 hertz divided by fs. So it's just direct mapping. There, yeah, I believe that's just about correct. And then we can create the this 0 pair. I do it. Yesterday I created 1 0 and then I actually added another one by making the complex conjugate. I can also do the same thing by putting j semicolon minus j. So that basically makes a complex conjugate pair. J times whatever angle you have here will be on the first row, and then minus j times the same one will be on the other one. So it's complex conjugate pair. Times omega z. There. Those are the points. Let's see, I think I need to do package load signal again to plot the z-plane of this one. ZZ. So those 0 points are now exactly on the angle of corresponding 120 hertz, which means that the amplitude response should go to 0 at those points, and we can calculate it. So okay, so that's fs over 2. Here we have the 120 hertz. So I'm expecting to have the amplitude response going down there, and I'm also expecting to have something like this, since we don't have absolutely no control on the this amplitude response anywhere else. Let me show you that I'm somewhat correct. So now we can do the this system coefficients. Same way I did it on yesterday. Polynomial which is defined by the zeros. So these are the system coefficients. Half of them. Okay. We don't have the feedback term yet. No poles, or actually poles are all in origin here. So basically, those are the parameters, and as you can see, this is kind of nice. So it's a 1 and 1 term. Then this term seems to be the one which actually turns the angle here. Yeah, makes sense. And now we can calculate the frequency response. PB 1024 points, and then the sampling rate. There. Excellent. So that point here is exactly at 120 hertz. We can actually zoom it zoom it there. Yeah, 120 Hz has the highest attenuation. Fine. It's just that the the calculation accuracy is just few points here, so it's shows that it would have say 70 dB, but actually in reality it's minus infinity dB attenuation, total attenuation at that frequency. However, I need to point out actually this thing here. If the frequency was not that 120, but say 117 Hertz, we have only about 45 degrees. So it's very narrow. So it has to match exactly the frequency. Or if so, for some reason, my sampling rate was not the one that I thought it was. For example, you're using microcontroller clock with the 20% accuracy. Your filter sampling is totally wrong then. Yeah. It would affect quite a lot. Let's make a difference, say. Okay. Oops. Typically, actually, these clocks internal clocks are usually on, say, good quality processors around 5% accuracy. So, for example, it was 5% off, like that. So we just multiply the sampling rate with the 1.05. That's why 5% higher frequency on the sampling clock. And let's see now where now we have at 120 Hertz we have only 35 dB. It might be enough. 35 dB is already how many bits? It's about 7 bits or something like that. Yeah, 7 bits. If it's not enough, if you had really high accuracy A to D converter, you just lost 7 bits. Okay. So there's another problem on that picture was that it's not unity gain. So this is not unity gain, and there's quite a lot of skewness. So you have on a pass band, this is supposed to be pass band, you have 18 dB attenuation even there, and then we actually have something like 5 dB amplification there. Not good. How to fix that one? The easiest fix is to add a pole somewhere in there. Right. Let's then remember something from yesterday. Yesterday morning about responses. About responses, how the frequency response is actually calculated. Or in this case, we have the, say, amplitude response is calculated. There's B0 divided by A0. Well, I'll just deal with that one. Just E to J omega minus Z1 E to J omega minus Z2 a e to j omega minus p1 times e to j omega minus p2. Let's do some approximation, and I will just make there's the 0, that's the pole. Let's consider that actually this distance here is the same as our point's distance. So this is the e to j omega right there. Same as that distance. Those distances are equal. Okay. On this point, this distance, since here you have a 90-degree angle, it's roughly, well, it's kind of, it's almost triangle. So there's A. So this distance is square root of 2 times A. It's just geometry. Okay. So on that point, e to j omega, that's pole 1. E to j omega minus g1, the distance is A. That distance, well, it's here. I just mark it B. So this distance, the long distance, actually, from this point to that point, that distance would be B. Then we have the distance to P1, which is square root of 2 times A, times distance from this point to that pole. It's roughly B. Roughly, not exact. This is engineering, not science. So this is 1 over square root of 2. So amplitude response at that point is 1 over square root of 2. Meaning this point is minus 3 dB point for the filter. Another point here. So after adding these couple of poles, you basically have something like this, such that you can actually control the half width of the filter. So there. So that's the f minus 3 dB, f minus 3 dB on both sides. Good. So now we can actually have a select our desired the 3 dB width or half width. So for example, if we want to have a filter with 20 Hertz full width, then we actually calculate the half width of it for the 3 dB point and calculate this angle. Remember, this is unit circle. So this distance is also the same as the angle. All right, so let's calculate. Okay, for example, 20 Hertz bandwidth. So we have A not AA, single A. I will just call it A 3 dB equals 10. So this gives 20 Hertz bandwidth. Half width is 10. So omega, the corresponding angle would be 10 times or 10 divided by Fs times 2 times pi. So that is the corresponding angular frequency. So now we know this distance and we know the ratio of the radius from the origin, which is r1 minus a. And we know the coordinate of the pole. So the coordinate of the pole, so pole pair, is actually 1 minus omega a times 0. Yeah, remember this was just the e to j omega. This is on the same angle but different radius. There, good. So those are the poles. Then the corresponding the polynomial coefficients or system coefficients are those. Nice, almost the same as the zeros as it should be, since the zeros and poles are almost at the same, but not exactly. So now we have A and B. We can actually calculate the frequency response. With real clock frequency. Oops. Not A, but A. There. See. Now we have a perfect band stop notch filter. I will blow up a little bit. And 120 Hertz is here, so minus 3 dB is about here, so it's about from 110 Hertz to 130 Hertz. Okay, so we can do paper and pen design of this one single filter. So we can actually take off the notch as long as our, well, the sampling rate is known and the frequency what we are trying to filter out is also known. Okay, good. Excellent. Let's move on. So that was the band stop notch filter. Same in animation. All right. The second easy solution to basically design these IIR filters is just to use the classical filters, and they have the counterparts also in digital domain. So these are basically analog filters which are transformed into digital space using bilinear transformation and some correction for the skewness of the frequency space, so that the we get what flat so that we get the cutoff frequency correct. Okay, And fundamentally, these are the three filter types that are enough. And those are the corresponding amplitude responses. Butterworth filter is maximally flat passband filter. It's basically just unity gain here, then it starts going like that. The problem is that the transition bandwidth is quite wide. If you want to have a better transition bandwidth, then you can tolerate, actually you must tolerate with some the ripple on the passband, and that's where you have Chebyshev filter. There are Chebyshev type 1 and Chebyshev type 2. Chebyshev type 1 filter has basically control on the passband ripple. Chebyshev type 2 has a control on the stop band attenuation. But that one, if you need control on both, then you go directly to elliptic, which is combination of having the control on passband ripple and stop band attenuation ripple. Okay. So basically, these elliptic filters are quite often used on the filter banks on audio systems because of the control. And these three filters here have the same order number, and basically, as you can see here, this would be, say, okay for most of the audio systems because of it has short transition bandwidth compared to that one, and still quite enough of stop band attenuation for most cases. Okay. Let's take a quick look on the octave, how to design those filters. They are so classical IIR filters. So there are these three, Chebyshev, Butterworth, and the elliptic. I think, let me take a help on the Butterworth. I think I remember that, remember the name. So butter, help, butter, oh, butter, not buto. Okay, there we go. Function on the signal package, so you have to do the package load for signal, and basically several different ways to use it, but this is the simple way of using it. Just B and A, and then the Butterworth filter design, nth order, so you give it an order number, and W is the okay cutoff frequency pi times WC radians. So okay, you need to give it a 0 to 1. This is actually not in radians, but this is on basically normalized between 0 and 1, meaning 0 is the DC and 1 is the Nyquist frequency. I know this is a little bit awkward for function to use. It's historic design. This was on the first signal processing toolbox of MATLAB in 90s. So this was the filter your father or mother used. But anyways, let's say IIR filter design. All right. Problem, how to guess the N. You can actually just eyeball it. Let's try it first. Just eyeballing. So we get filter coefficients BBB, AAB, like Butterworth, equals butter, say, fourth order and half bandwidth. We can also now check if the system actually gives me what I'm for. So this is order number of the filter, fourth order 0.5, meaning that its cut-off frequencies is the half of the frequency plane. So it's FS order 4. Should be. We'll see. Frequency response. BAAB. Yes. So at 500 Hertz, it starts going down. It goes to minus infinity. See, it looks like, oh, this is not a filter at all, but yes, it is. This, 100 dB would be already enough. Human hearing, hello, the dynamic range is only about 100 dB. Wow, of course, just like that. 100, okay. There we go. So it's actually pretty nice looking filter design, half bandwidth. Now, if you want, for example, that low pass filter at 200 Hertz, then you would have 200 divided by Nyquist rate. Okay, so I know this is a little bit awkward to use. So BB, so 200 Hertz would be 200 divided by Fs divided by 2. So this is scaled to Nyquist frequency. Okay, frequency response. There we go. So now we have a 200 Hertz, the cutoff frequency. There. Where's 200? Oh, there. Yeah, minus 3 dB point at 200 Hertz. Okay, and then how about higher order systems? Very simple to see here that if we take, for example, the 8th order, we can start eyeballing what is our desired the transition bandwidth here. Okay, there is a helping function. So Butterworth filtered coefficients are done this way, but there's also a helping function which helps you to find out the proper order number. And the proper order number basically is defined by one single point and the attenuation at that one single point. So cutoff frequency you can set. Then basically you can also define the stop and start frequency, meaning you can have control on the transition bandwidth here and the attenuation on that point. So for example, if you want 60 dB attenuation at, this was 200, at 300 Hertz, that would be a little bit, well, let's make it 500 Hertz. 500 Hertz, at 500 Hertz you want 60 dB attenuation, then you can actually use the boot-ord to calculate the number. Okay, so how to use it? It gives the order number. Okay, passband frequency normalized. Stop and start frequency normalized. Ripple on passband, meaning, okay, 3 dB points. This one, 60 dB. Passband, stop and normalized Nyquist frequency. Yes, to the Nyquist frequency range. ARP is allowable passband ripple in decibels. Minimum attenuation at the start, the stop band start. Okay, we can use that one. So we calculate the order number with those parameters. Butord. We had, okay, before that one, let me calculate the Nyquist rate or Nyquist frequency, because we will be otherwise making probably some mistakes there. N equals to Butord 200 divided by Fs. That's the 3 dB point. So band pass the corner frequency of the filter, Lopez filter. Then it has the WS is the 500 hertz again, not Fs, sorry, Fn, comma 500 divided by Fn. Okay, now we have the frequencies already in. Then we need the passband ripple. So we calculate the 3 dB point and then the 60 dB attenuation at that point. 7th degree. Yeah, that's great. It's still, let's say, a reasonable number. If you start to get 100 or so, then forget it. You have something wrong. You cannot make it that steep. Yeah. So this should be, say, up to 10 or so. That's still doable. And now we have the order number, and we can then design the filter. Right. So we have the NN, oh, not NN, with the cutoff rate of, let's make this one also the Fn. There we go. And frequency response, just to show that it is really that. Okay, I said 500 hertz. So at 500 hertz, we should have this 60 dB. Yeah, yes, it is. It's at least 60 dB attenuation at 500 hertz. Okay, so this pair, Butord gives you the order number, and then this Butter gives you the these parameters, system coefficients. Same thing for Chebyshev. Let me take again the help of Butter to see what was the function name for Chebyshev 1 filter. Oops, forward. At the end, there's supposed to be no, it does not have the reference list. Let's find it from the Octave reference. Okay. It has also okay package list. signals. Where is the dependencies? Function reference for signals. So here we have basically somewhere we had correlation for filtering, filter analysis, filter coefficient. Okay, there we have IIR filter design. So in Butterworth we have these functions. In Octave we have these functions to generate. So we use just the generate Butterworth filter. But or compute the minimum filter order. Okay, good. Then we have CHEB1. Compute the minimum filter order of Chebyshev type 1 filter with the desired response characteristics. So this is basically same as for the Butterworth, this but or, and then basically CHEB1 app is design low pass analog. No, analog. Where's the Chebyshev one? CHEB1. Okay. That's to generate the filter coefficients. Same for elliptic. Ellipod and ellip. So let's go back to Octave and say, what is CHEB1 odd? CHEB1 odd. Okay, so we can calculate that order number. Order number for Butterworth design, same parameters. CHEB1 order. Okay, see, only fifth order needed because Chebyshev is steeper. You allow some passband ripple, you can actually gain something on for the transition bandwidth, and we can use lower the order number. And then I calculate the BB and AA using not Butterworth but the CHEB1. Let me take a look at AAC, AAB anymore, AAC and BBC. And let me take a look at the help files here. Help for Chebyshev 1, it has actually N ripple, and then so this one has one more parameter compared to Butterworth. So there we have, I also should include the ripple here, and I had 3 dB ripple. So basically on this Chebyshev ripple is one of the parameters. So basically 3 dB ripple is quite a lot. So usually basically on audio that should be say 2 or less. Okay, there we go. And let's check it on new figure. BBC, AAC, sampling rate, and oh, wow, that's cool. See, that's basically the same filter design as that one, but with the different filter type. So left-hand side is Butterworth, which has flat response here. On Chebyshev, we actually let the this passband have some ripple on it. So we have 7th order filter and 5th order filter, similar the transition bandwidth properties. If we can tolerate that ripple on the stop band. The same actually goes also with the this elliptic filter. There, let's go back a bit. Elliptic, ellip odd. First we calculate the order number. So, okay, same parameters as but odd. Okay, and then we can use that one in to calculate the coefficients. Okay, passband ripple, stopband ripple, and the cutoff frequency in that order. There we are. Okay, Cheb. That was ellip odd. Order number for elliptic. I give it the same report as for Chebyshev and this sign value for the 500 Hertz point. In this case, it will be actually the okay. And we go down again. So the Butterworth had 7th order, Chebyshev 5th order, and elliptic has 4th order system, depending on what you are looking for. If you can tolerate about those the ripple on the passband and what kind of behavior you want on the stopband. Okay. And next we calculate the next we calculate these coefficients. Ellip 60. Yeah. So elliptic design parameters with this order number, 3 decibels of ripple on the passband, 60 attenuation stopband, and then the same cutoff frequency. Ta-da! Third figure. There. I wish you see this. Okay, there we go. There we go. Okay, so that was the Butterworth, flat, 7th order, Chebyshev 1, ripple, but 5th order. Okay, this is the elliptic, ripple here, stopband attenuation is actually below the 60 dB, so it doesn't dip down to the infinity, and this is within the design, and we got we got basically 4th order system, 7th compared to 4th. This is more cost efficient. Remember this difference equation. When you start calculating these numbers, 7th degrees AIR system has 13 additions and 12 multiplications. Is it right? Right? Yeah, something like that. This has roughly half of the amount of calculations as that one. Good. Let's see what is next. Okay, it was on the function reference. So we were on the classical filters. Okay. The zero phase implementation. In case you need a filter or data post-processed so that there is no time delay on the signal. So basically you can take the system of the signal, run it through the system, then reverse the time, then basically filter the signal again, and then reverse the time back. Then you don't have a zero phase difference. What I can say. Good. Only if sometimes you might actually need it, but well, I have never actually used it in real life myself. This is non-causal and works only for post-processing of data. But if you need it, it is available for low price. Just mentioning a median filter. Median filter is actually one which is used a lot in image processing. Not that much anywhere else. Basically, it's quite smart system. So think of a signal, 1D signal first. Just make it. We have a lot of samples, and we don't have that many. Or we have a slowly varying signal like that, and then we have missing data points. Oh no, it happens. It happens actually when you are measuring data. We have a missing data point, which means it is either zero or a spurious peak, a snap. Something happened. The transmission fault or something like that. That's not good, since it shows up immediately as an anomaly. With the median filter, you can actually get rid of that. So median or 3-point median would be the center value. You take a 3-point median, you take 3 points and put those on order, and what comes out is the center, the midpoint of it. So in this case, it would be those 3 points would give this one as output. Those 3 points, that is the output. These 3 points is this. That is the output. These 3 points, well, that is the output. These 3 points, we are back to the normal 4 points. Okay. Which means that this kind of spurious peaks actually disappear on median filter. Really effective if you have just singular spurious peaks on your data. Works like a charm. And it's used especially on the image processing, since you have dead pixels in camera or display. Well, display doesn't much mean anything, but the dead pixels in camera, you can get rid of those like that. It doesn't show up as a black dot or a bright spot. Okay, so there's a short animation like that. So think of that red square here on an image as a bad pixel. So if we calculate the 3x3 median here, most of those values are this gray. So it means that that's also the mid value. So we just replace that point with the median of the surrounding pixels. It really gets rid of this kind of speckle. All right. So that was the median filter. Then another special kind of thing is matched filter. meaning if you have very weak signal and you are not totally sure what it looks like, but you have for example, in radar technology, you can measure the pulse, radio frequency pulse, what you are sending. You do not have actually control. Since it's high powers, it can be kilowatt, actually megawatt range, the peak power on these radars. Okay, but you can measure the waveform. Well, the same way as you are measuring what is coming in. You just get one part of that signal when it's going out. If you know exact form of what you are sending, you can actually generate filter coefficients which match exactly what you are expecting to receive. So you are basically expecting to receive the same signal. So you can use this data and make the time reverse of it, so it will be actually filtering the input. So it filters exactly the same way, or it separates the reflected signals from the input data, if there are any. So that's actually have the optimal signal to noise ratio then for the receiver. So radar, here you have the power electronics. It's black box, lots of power. So okay, that sends a signal like that out as output. You are measuring it. Looks like something like that. Then you have here the enemy aircraft. Of course, it's enemy. Let's see which way your enemies are coming from. Okay, let's not make it political. All right, so send that one, you get the reflection back, tiny amount of reflection back, but you use this one as on the h of n for the filter. So basically this is same as the b parameters bb, or actually h of minus n is the same as bbn. Time reverse, it's then basically the input signal has a lot of noise. Nobody knows what happens there. So that's h of n. When you put that one inside of the system, which has this bbn as the system coefficients, what comes out is basically and then some the response from this aircraft. Okay. So that's how the modern radar actually does things nowadays. The or well, not just this kind of radio frequency radars, but also sonars, so sound radar, or a depth finders, that kind of things. Basically, in here you have unlimited resources and lots of power, but say, for example, parking a car, you don't want to use too much power on acoustics. Or on a sonar, you don't want to put too much power on your sonar either. So with the with efficient signal processing, you can actually lower down the power. Okay, good. So basically, that was the theory part. I will then just continue with something, since we did not cover yet the how to do design for high pass filter, or the high pass filter, or or bandpass filter? Well, read the manual. So basically, you can turn this same elliptic filter to high pass design by simply using the same order number, ripple on passband, stop band attenuation, cutoff frequency, and just put it high. Okay, band pass filter, same things, and just have the lower cutoff frequency and higher cutoff frequency. I will show you how to do it so you can actually tolerate the exercise then. Okay, so let's go to see this one. So high pass filter. Example is just this. Let's take that elliptic. Keyword is just put high at the end. Was it actually in double? Where's the? Yeah, okay. Yes, it is. That's actually those. All right. I'll just make this one H like high pass figure. Okay. You should see this. So that's the high pass. That was the corresponding low pass. Okay. So you define the cutoff frequency, which here is 200, same as here. With these two filters, actually, you can start already doing some, tone balancing. So lower frequencies, higher frequencies. If you put different gain for those bands, then you actually are already doing this kind of equalizer or something like that. Okay, that was the high pass design. Then the band pass design. Let's mark it somehow. BB band pass BB band pass, and it had actually two cutoff frequencies on here. So you had, for example, like this 200 and 300, oh, let's say 400. 400 are the cutoff frequencies. So now if you put it like this, then that will be the first cutoff frequency, that's other cutoff frequency. New figure. BB band pass and no magic here either. So we have the that looks like actually the double the order number now. 1, 2, 3, 4. No, it is still the no, yeah. So this actually doubles the order number. Okay, so like that. So we have a bandpass filter design from 200 to 400 hertz, and then let's see, band stop, same as that one, but you will basically just define it as band stop filter figure. There you go. Same but band stop. So you just call the same function differently. It gives you different the behavioral filter. Good. Okay. Then small hint to today's exercise or the fifth exercise. I think nobody have time to study today yet. You probably should be working still on say either the second exercise, maybe third exercise. I know you need to also sleep, so limited time, and that's why we have the deadline. So deadline for the first exercise is today. As long as I am here, I'll be leaving at 5 at latest. So before that, I expect every one of you to have the return. One group has already done the first 2 exercises, actually. Okay, so, but anyways, let me give you some pointers for the exercise. Some pointers. Exercise template. That's 5. Okay, here we have the design band stop filter with the following properties. This is for, this is the notch filter. So that's the where I started, which is the that one. Notch filter. Single, 0 pair, and on the same angle you have the pole pair. Then plot zeros and poles. You know how to do it. Impulse response 21st values. And then basically this is using one of those filter methods, Butterworth, Chebyshev, or elliptic, whichever fits into this one, and design a low-pass filter based on these. And verify your design from amplitude response graph. Good. Compare. Okay. On the FIR filter, you had the same design. Now you should actually compare the major differences and a pointer what kind of things what you would expect. Difference is the phase response. Linear, non-linear. Of course, this is non-linear, but that's obvious. Another important place is what is the order number? I'm expecting that this IIR filter has much lower order number. Okay, then another design high-pass filter. Okay, and then basically on 4.7, okay, there was a some sort of okay, on 4.7, so previous exercise, there was basically filter characterization, what you should have been doing, what are the requirements. I think we need to go back to that one to see what it was, and then comparing. Then design filters, either IIR or FIR. I probably would do it on IIR. For 3-band equalizer. Oh, right, that's what it looks like, a system level. 3-band equalizer. On spectrally, there are 3 bands, 200 Hertz, then 2 kilohertz. Well, you are hearing somewhere at 20 kilohertz. So our sampling rate is now 44.1. So Nyquist frequency is 22,050. So basically, this is the bass, low frequencies. This is the middle band from 200 to 2K, and then we have high pass for high frequencies. And what makes this one equalizer is simply that you adjust the gain on each of these filters. So you have 3 filters and you have 3 different gains. So how to make that tone adjustment of music is that you have one single source for the music. Then you have 3 filters. The same signal goes through 3 filters. So you have the bass filter, mid frequency filter, and then high frequency filter. And for each of those, you have variable gain. And then you sum the output. Okay, there we have. Adjustment for bass, adjustment for the mid frequencies, and then adjustment for high frequencies. That's a 3-band equalizer. Nothing fancy about it, right? Okay, but anyways, now it's a lunch break. Time for lunch break. After the lunch break, I might actually also show you some pointers, more pointers on how to handle the audio data, like how to get your favorite song into the Octave if it's not WAV file, and then basically how to do some filtering for it. Since I have already some filters here, I can simply show that it works. Okay, but anyways, now lunch break until say 1:30 ish, and then I decided actually at about 3:30 I have a special lecture about Finland if you want to hear something about Finland. So this kind of like relax at that point. But anyways, now lunch break.